What's that? Okay, I'm going to speak about alarm correlation. This is a new feature coming forward. My name is David Smith, software developer at OpenNMS. Software developer at OpenNMS for a total now, I think, of 6 months. So pretty brand new with the product. Dealing a lot with the levels of complexity that David spoke of earlier today. There's a lot of different wheels and hubs and sprockets moving in the stack, but for the 6 months, I've been pretty much focused on this with 2 other people in the Ottawa office of OpenNMS. So hopefully I'm in a position where I can speak at least reasonably about alarm correlation. What is correlation? So the whole idea of correlation is that an operator can be looking at a screen and seeing thousands upon thousands of alarms rolling and scrolling and stuff like that. Correlation, it says that some of these are related. They're correlated. It happens because, for instance, somebody kicks the outlet or plug on a switch, and hundreds of alarms happen all at the same time. Well, they're really happening because of that one reason, that somebody kicked the switch. So wouldn't it be great to see one alarm as opposed to seeing 100 of different types too? Because the alarms might say, there's a minor problem about this, there's a major problem about this, critical problem about that, whereas a situation, which is what we term for an alarm that contains all the other alarms, is of a certain critical severity because the switch is gone, because somebody unplugged it. And hopefully at some point we'll be able to tell them, the possible remediation. So if we see the entire switch light up as a Christmas tree, we can probably see that there's a fault with that switch. And so that's the whole goal of this feature, is to shrink the stack of alarms into a more easily digestible list of situations. A situation is just another alarm, same as all the other alarms in OpenNMS, except for the fact that it points to other alarms. So it has a property called related alarms that says I'm related to, or basically I bundle this alarm, this alarm, this alarm, this alarm, and this alarm. And that means now you can just refer to the situation and have all the other alarms as a reference. And this can be done one of 2 ways. You could take an existing alarm, say that, for instance, when the switch goes offline, there's some monitoring device that's polling that, and it sends out a syslog message that says, switch A is offline. Now, if you wanted to, you could just use that alarm as the situation, and then attach all of the other alarms to it. So then you have a switch offline alarm, and all the other alarms that are triggered by it, which could be links down, services down, everything, under one single alarm. The other alternative is to create a new clean alarm that contains all of them. And that's what our engines actually do. And I'll talk about the engines and the correlation engines very shortly. To highlight the benefits of the alarm correlation, why we're doing this, it's a sponsored project. The customer that is asking us to do this wants to remove this existing functionality from their network from another vendor that charges lots of money for it. So the reason they have it, though, is because it reduces noise for the operators. So they're watching a pane of glass. As David said, you can actually roll up multiple OpenNMS systems into a single Grafana Helm UI. You can be watching a whole bunch of things. But again, if the volume is such that they're drinking from a fire hose, it just makes it very problematic. So what this can do is it reduces the noise. You're just seeing those that are rolled up into situations, so they're all containerized. And it can also prioritize the workflow. A situation can have, and by default will have, the highest severity of all the alarms that it contains. So if you get a whole bunch of minor issues and they roll up into a single situation, that would be a minor situation. If you have a situation that has alarms that are both minor, major, and critical, the severity that contains them will be severity of critical. So feel free to interrupt at any time, interject with any questions. I'm going to, yes? The question is, can situations be acknowledged? So as I started off, and we'll come back to, a situation is just another alarm in an OpenNMS context. So anything that can be done with an alarm today can be done to a situation. We have a set of behaviors and rules in our alarm D daemon that will process that. So if you acknowledge a situation, it will actually cascade and acknowledge all the alarms that are contained into it. So, very good question. Hopefully that answers it. Okay, excellent. How do we do this? How do we do correlation? Another thing that you saw on David's slide earlier today was the very broad topology of an OpenNMS deployment, what it can entail. Currently, the OpenNMS correlation engine, we'll reference as OCE at certain times, will be one more component in that. It can reside within a Sentinel container so that it makes use of the exact same load, high availability that other components deployed within Sentinel can. And it makes use of the Kafka bus in order to send messages to and from the core component of OpenNMS in order to read in topology updates, read in the alarms that are coming in, and then return to OpenNMS the situations that it creates. So basically what ends up happening is you have this stream of alarms coming in and a stream or individual situations, which are new alarms, going back to OpenNMS. The correlation engine, the OCE, is defined as an interface. It's a very simple one. Basically, in order to initiate it, you send it all the existing alarms, you send it all the existing situations, and whatever your topology is or your inventory. And then within that, it has its logic in order to do everything. It's driven by a driver, and a driver just on a regular timestamp tells the correlation engine to do its evaluation, and that's what the tick is. By having that, one of the things that we can do is we can take a canned set of alarms, push them through the correlation engine as though they were happening in real time. So we can take a week's worth, a month's worth, a year's worth of alarms and actually push them through a correlation engine and just tick, 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 tick. So we would actually be able to evaluate what happens, how would it do its correlation and stuff. And the framework in order to do that and the test framework that we have in order to validate our engines has been very, very useful in that. One of the things that the correlation engine must do as well is register a situation handler or allow for the registration of a situation handler. So that's its way of sending the situations back. So once it decides that the first 4 alarms are in fact a situation and should be bucketed together, then it will use whatever's been registered as the situation handler in order to deliver that back. So with those 3 simple methods of the API, you can basically design your own if you wish. Like if you have certain rules and logic that you want to apply to correlation, you can do that. Or you can use existing. We have 3 existing ones right now. We started off to determine what was the best way forward. It began with a proof of concept, as I say, the hello world of correlation. And what this one does is it's just a simple sliding window. And there's knobs and buttons you can tweak for the amount that the window slides, how long it stays open, or if it's just a hard window. And what this means is that if it sees 4 alarms come in all at the same time, then there's a good chance that they came for the same reason. I mean, especially you would think intuitively, if they all came in at the exact same time, something on the network probably triggered that. Otherwise, they would happen at different times. It's actually surprisingly accurate because a lot of the stuff on the network is triggered that way. That a lot of the stuff that happens at the same time is happening because of the same underlying root cause. But it's a great proof of concept. And it's a real easy way to see how things would get correlated in your network. And as I talked about before, because we have the driver that would let you replay events, you can actually test it out and see how it would do. You can change the size of the window. You can say, if all of these happen within 100 milliseconds of each other. Generally what we found in that case is that stuff would really get separated. A sweet spot of about 60 seconds or 1 minute tended to really correlate things, whatever happened. It also depends on the size of the network. Obviously, a larger network is going to have more overlay and collision. Anyway, so the next much more complicated engine that we worked with was a rules-based topology engine. This uses your network topology, some of the stuff that Antonio was just talking about, in order to determine are these related. And it uses rules, JBoss rules engine, to set out how you define a correlation. I put up an example of one of the rules, and this would drive a card down situation. So it would take existing alarms, put them together. The point of putting up this was, I hope it looks really complicated. The rules engine based topology or based correlation engine is really complicated. What ends up happening is you have to write very edge case based rules in order to cover all of your scenarios. It also relies on your topology being very correct. If you take off, a segment of your network, you really need to tell the correlation engine, otherwise it doesn't know what's up. Similarly, if you add new equipment, all of that addition and subtraction of network nodes can play havoc on this. We still have it working, we still have it in our test framework and validation scenarios, but at this point we're not really pushing much further on it. What we are doing is doing a cluster or graph-based engine. This is currently deployed at our sponsor site and is doing yeoman service of correlating the alarms that they have. It's graph-based. It uses dbScan as the machine-based algorithm. So what it does is it places alarms attaches them to nodes in the graph, and then it uses the distance algorithm of basically hops away from that vertex and the delta in time. So it kind of uses a combination of the first two engines, both time-based and location-based. So it makes sense that if at the exact same time a network switch in Germany and a network switch in China went down, maybe they're not quite as related. There's a large distance from them possibly on different IP networks, for instance. However, if they had a link between them, then we would know that actually, yeah, there are actually two ends of nodes. The fact that they went down at the same time, there is probably some correlation to it. Or if the link went down, there's some correlation to that. So that's it based on the distance in the graph, that distance being calculated both space and time. One of the other things that this does is it attempts to extract elements from the topology to create a vertex. So basically, as a syslog message comes in, as an SNMP trap comes in, it tries to create or abstract a model object from that. So we have logic that will take a switch IF index and a switch port name and hopefully try to correlate those as well too. So that it says if this SNMP trap comes in and this syslog comes in, then we can actually determine that they're actually on the same object in the network. So we don't actually have to have an accurate network, but we just have to accurately be able to say they are in fact the same objects within the network, not having to know the entire network. How many people have used Helm so far? Anybody? Good. This is a snapshot from it. I know there's a presentation on it tomorrow. Jeff will be pardon? Oh, Helm, yes. It's okay. I don't do it either very well. I mumble a lot and interrupt me, please. So this is a dashboard created in Helm. It uses the fault data sources to display alarms. And what we've done is we've created 3 tables here. One shows alarms that are not in a situation. One, it shows just the situations. And one, it shows all the alarms in situations. We've also chosen some of the new columns that are applicable for situations in the situations table to show interesting things about that. So instead of showing which node they're on, because they could affect multiple nodes, we show the node count and we show a situation alarm count, which is basically the number of alarms that are rolled up into that situation. not counting the situation itself, which is also an alarm, to make things confusing. So currently, this is the only way to visualize the situations. We don't have anything implemented on the basic, the green OpenNMS UI screen, but that'll be a TBD. The functionality that I've described so far is all part of 23, I believe, and the core functionality that builds on top of that should be out in Horizon 24, is my understanding. So here's how we made some of these tables. We have the ability now to filter all of the situation stuff. The whole idea of situation as alarm means that it adds on to our alarm REST interface. So everything in Helm uses the REST interface in order to pull data and render data. So now we have a couple of extra attributes that we're able to filter on in Helm. So you can see that the middle table was just facilitated by using the where is the situation is true. So it's as simple as that. And then you have all of your situations filtered out. Or if you wanted ones that aren't, conversely, you could just set it to false. Here, there's a similar sounding but substantially different one is in a situation. So if we go back one, you'll see that the top alarms are not in situations. That means that these alarms have gone through the engine. They have not been correlated. So they might have been one-offs, spurious here and there. They could be for any reason. And then it was the second table that was created. The extra two columns in the situation table can be done this way. Affected node count is now, you can actually filter on that. If it's not equal to 0 or 1, so it's anything greater than 1, will be displayed. Similarly, alarm count could be filtered on, and that allows for that. And I spoke to this already, that there's a extra alarm count and affected node count. So what happens when you click on one of these situations to look at the details for it is the extra tab in the alarm details page will be rendered. The way it's configured, it has the label of, so this situation now contains these three alarms. There's alarm A, B, and C that were triggered. By the coloring, you can tell that they were all critical as well. And you have the same link to the OpenNMS alarm detail page if you wanted to drill down and visit any one of them and see extra details. That's about it. The related alarms tab will show if there are related alarms, and it just won't appear if it's not a situation, if it has no related alarms. There's also the submit feedback part. That allows us, currently the dbScan is untrained machine learning to do the correlation. The idea with submit feedback allows the operators to say, yes, these three alarms are correctly correlated. This is perfect. Or it could say, two of those are right, but one of those is wrong. Or it could say, none of these are right. And what that will do is it'll actually persist feedback that we can later use to train the correlation engine in order to improve its results. Situation feedback. As I said, it allows the training. It also removes alarms from a situation via Helm and or the REST interface. It actually allows you to add an alarm to a situation. You can say, here's an alarm, a UEI for an alarm, a reduction key, and say, this should have been in this situation. And the REST interface will actually allow you to do that, to hook them up. In Helm, you can only give negative feedback and take one out. So this is what it looks like once you've clicked on it. If there's already existing feedback, you'll see an indicator that say resubmit feedback, because you can always add further information and training to. But otherwise, the three alarms that we saw displayed, you'd have the ability to say, for instance, click on the red X, which actually doesn't display very well up here, but you can see that there's a filled in circle around it. Saving this now would then submit the feedback for these three alarms related to this situation or contained in this situation, persist those. And because this one was given negative, it's basically a false positive. it will submit that as well too. And the situation, which is stored in the Postgres data store, will be modified. So it's no longer related to alarm A. So if you go and look at it, or another person goes and looks at it, a situation will only contain 2 alarms, B and C. Feedback currently is persisted in Elasticsearch. And as I mentioned, the goal of persisting that feedback is to train the AI to do correlation. Any questions to this point? Yes?
Does the persistence of the feedback to Elasticsearch imply that the AI is using Elasticsearch to learn?
It needs to be wired. So at this point in time, it's not. As I mentioned earlier, parts of these are being deployed within 23. Parts will be deployed in 24. So what we've done now is we've put a marker in sand and said, okay, we need to persist this feedback somewhere. We need to do something with it. So the idea is that we've created an API. We've exposed it to the REST endpoint. So you'll be able to set feedback, both false positives, false negatives, and correct feedback for any alarm in any situation. Then you can also retrieve that, and so that's why you would know you're resubmitting feedback, because every time you go into Helm, it actually extracts any existing feedback for that alarm. So Helm is using it right now. Our clustering engine is not, but the ability is there because we've exposed it through the REST API. Storing it in Elasticsearch is a decision that we've made now, but it could easily be changed, and then it just remains exposed to the REST API at this point. Thank you. David's earlier slide talked about complexity with the OpenNMS deployment. This functionality is currently depending upon a bunch of wheels, a bunch of cogs and sprockets in an OpenNMS deployment. We tried to self-contain as much as possible, but there are a couple of requirements. One is for the feedback, we need to be running Elasticsearch. For the correlation engine, we need to be running Kafka in order to have the alarms from OpenNMS go on to Kafka bus using the Kafka producer, be read off by the correlation engine, and then situations are put back on to a different Kafka topic in order that the OpenNMS will then pull those in, see them as events, and create the alarms. So the components of the actual feature, though, the correlation engine, are basically just a driver. That's what drives the overall correlation, that tick that we saw. It will keep that running. The actual engine implementation, which to this point can be one of 3, one of 4 if you write your own, and a data source. And the only data source we have right now is the Kafka bus, and that does it for alarms. And I must have done this for Antonio Situation Z. So in order to deploy it, basically you have to download Docker image of Kafka is probably the fastest and easiest way to do that. We do that with Spotify Kafka. Enable the Kafka producer feature and the sync API. Those are both documented on the admin docs of the OpenNMS product. I won't go into them here. I like to keep this more of a high-level overview than drilling down details, but I do want to give you a bit of a recipe. So if anybody wants to actually do this and they get stuck, they can contact me afterwards. Yes?
To reduce complexity, couldn't we just embed Kafka in OpenNMS?
Yep. The question was, can we embed Kafka in OpenNMS? And sure, we can. Yeah. And that may happen for the final packaging for this feature. I don't know. I'd have to talk to bosses and product management, everything else. Anything's possible. It's just software. It's just bits. We can do anything. So for the actual installation, if you want to build the correlation engine, it exists currently in its own OpenNMS repo. So clone that source, build it with Maven install, and then use the Carafe shell to install the features. Again, just those 3 features: data source, an engine, and a driver. And this is a little bit more canned version of a recipe to do this. I missed it to do in my slide deck. And the answer is no, it doesn't work with a local deploy because we don't have Kafka deployed locally at this point in time. But otherwise, feature install will do that. Further reading, so coming up, so the docs are actually a work in progress, but you will find information on this within the coming weeks in the admin guide. The developer guide will cover the REST API, so that's what sends the situation feedback in, gets the situation feedback out. Also changes for the alarm REST API, because now we have not a whole lot, it's just an extra attribute on the alarm that says, you know, here are related alarms, and that would basically turn that alarm into a situation. There'll be a bunch of changes in the Helm guide that show how to filter, create tables to show only situations, to create tables that have alarms just not in situations. The GitHub link, as mentioned on the previous page as well, will show you that. And then there's a wiki that we've started with some of the design architectural information under Project Sextant, which is the sponsored project for the alarm correlation. That's it. Thanks for listening to me.